Hello, very happy to see you here. It's Ava. I'm your algorithms and data structure teacher, and thank you for all of you who joined. I'm really happy to see you here, really happy for us to start. And today we are talking about time and space complexity. So if you ever heard the words throwing around, n log n, O of n, exponential, logarithmic, of and square, people are talking about either time or space complexity. So first of all, let's make sense of n. What is n? People are talking all around about. N is when you write your program, you have an input, and this input could be an array or a string. So the length of this array or a string we would call n. And we will measure, if we are talking about time complexity, how fast or slow our program runs depending on the length of the input. The best time complexity ever is constant, is when your time it takes to run your program is totally independent of the length of your input. Your input could be billions. Your program always runs in the same time. If your dependency is linear, if we are talking of n, if you increase your input 100 times, time of your program increases approximately 100 times. What about n square? It quadratic of n square. If your input increases 100 times, your time increases not 100, but 100 squared. It's 10,000 times your program would be slower. No wonder people don't like often square time complexity. Now you know. Next, and when we talk about it, we don't care about the constants. Of n, of 5n, of 500, 5 million n, still of n. In reality, it makes a difference, but in computer science, we only talk about the relationship. So it's still of n. Let's talk about space complexity. Space complexity is how much memory your machine uses, your program uses, depends on, again, the length of the input. There are two main sources of space complexity. You either create it yourself when you create your variables, when you create your arrays, matrices, hash tables. This is very obvious way. You probably noticed it already. If you create an array and put n elements there, and it's the same as length of your input, you would have often linear space complexity. The second source of space complexity is slightly more tricky, is the stack of recursion, depth of recursion calls. So if you call your function recursively, for example, you call your function recursively n times, computer would need to remember where to return each time and what arguments the function was using. So it would need space for this. How much space? How many times you call the function? Yeah. So yeah, for this we would need some extra space. If you're listening right now and it does not make a lot of sense to you, don't worry. We would get into the details. We would see some examples and you would see how it actually happens in real life. But remember, there are two main sources of space complexity: your variables and the stack of recursion. Okay, and if you are listening right now to this and you're thinking, why do we even count it? Why do we care about it so much? Computers are so fast. Yeah, it's the fastest computers in the history. Why do we care? The next lesson would be exactly for you, because I will teach you a trick which would shared by my friends who do Olympiad programming, who do competitions. We would all get on the trick when you look at a problem and you could predict how much time it actually would run. This is super awesome. So don't miss it. I will see you next week.